Thanks, Nestor. And good morning, afternoon, evening, night, everyone. Thank you for joining us from all over. And thank you for putting up with our relative lack of breaks in this session. Ryan, MacDonald, and I are excited to talk to you about the work that's been going on in subgroup 2 of SAG21, which is focused on stellar and planetary retrievals. So we'll explain what that means, stellar and planetary retrievals, who subgroup 2 is, and then we'd like to use our 25 minutes to communicate 3 of the preliminary findings that have been coming out of the conversations that we've had, and look at some other topics that we're also exploring in this subgroup before we submit our final report to NASA. So what is subgroup 2? Subgroup 2 is mostly interested in the impact of unocculted active regions on transmission spectra. And they do that through this phenomenon known as the transit light source effect or contrast effect. This has been introduced a few times already, but because we're like a diverse group here, I'm going to be a little bit pedantic and just explain it once through. So when we're measuring a transmission spectrum in the lab, what we do is we measure the spectrum of the light source, we place some medium in its path, and we measure the transmitted spectrum. We know the spectrum of that light source very well. But in the case of exoplanet transits, we actually don't know that light source as well as we'd like. Transits are this differential measurement where we're trying to get that initial spectrum, place something in the path, make the difference measurement. But in this case, the initial spectrum that's illuminating the exoplanet atmosphere actually comes from the spatially resolved region on a stellar disk in the transit cord. And we can't probe that emergent spectrum from that area directly. What we do is we take the outer transit spectrum of the star, which is from the entire disk, and we assume that our light source spectrum is that spectrum. But there could be differences due to active regions in the transit cord, which we saw discussed earlier today, and those produce blips in our transit profiles. Or there could be differences due to active regions that are elsewhere on the disk, and those are a little bit more nefarious in this context because they introduce this spectrum between the assumed light source and the actual light source that we can't directly see in the transit data. But that different spectrum gets imprinted on the transmission spectrum in a way that in some cases can mimic or mask spectral features coming from the exoplanet atmosphere. So at the end of the day, when we measure transmission spectrum, we're getting the combination of 2 signals. One is the change in transit depth as a function of wavelength, which is due to absorption or scattering of the exoplanet's atmosphere. And the other is this wavelength dependent contamination factor due to the heterogeneity of the stellar disk. So we are interested in measuring the planet's atmosphere and the degree of heterogeneity on the stellar disk through a technique we call retrievals, which Ryan will tell us about.
Can you hear me? Because I'm having some technical difficulties with my video.
Yes, we hear you.
Great. Thank you very much for that introduction there, Ben. So just to clarify some terminology here for anyone who perhaps isn't familiar with what we mean by retrievals, is essentially this is just a fitting exercise. Given an exoplanet transmission spectrum, such as this one by Laura Kreidberg from 2015, shown by the arrow bars here, we want to know what are the range of atmospheric properties that are consistent with this set of observations. And this is just illustrated by these probability contours here, showing us the range of model spectra that can indeed fit this spectrum. So if you just advance to the next part then. So how this essentially works, and I know this figure looks a little bit complicated, I apologize for this. Essentially all this is you can imagine a giant for loop. You iterate over hundreds of thousands or millions of potential atmospheric compositions for the given planet. So this could be varying the molecular and atomic abundances, the temperature profile of the planet, and various other properties. For each location in the parameter space, you generate a model spectrum, you compare the likelihood of it via the chi-squared, for example, to the observations. And depending on how good or bad a fit it is, that informs where the Bayesian sampling algorithm explores next in the parameter space. And at the end of the day, when you go through this exercise, you move forward then, what the output is a set of probability distributions for the various parameters underlying your model. So we want to be able to place statistical constraints on, for example, how much water there is in the planet's atmosphere. So this is all that we mean by retrievals, fitting the spectrum to work out statistical constraints on the underlying properties of the planet's atmosphere. And I'll just pass back to Ben for a few slides before we get to our preliminary findings.
Thanks, Ryan. So yeah, subgroup 2 is focused on this technique of using these inference frameworks to constrain stars and planets simultaneously. And in general, the question we'd like to know is how can we best combine the information we get from stars and planets as in the techniques that we've seen so far today and that we'll see some more of tomorrow. How can we combine these techniques with our transit observations from space-based facilities to extract the most information? I wanted to recognize that there's been a lot of interest in this and a lot of the contributors from SAG21. So thank you all for your input. The subgroup is being led by Joanna Barstow, who couldn't join us today, Ryan, MacDonald, and myself. And we've had direct contributions so far from many people who had participated in the conversations. And we're looking to continue this conversation for the next few months as well. So now we'll move on to the first finding from subgroup 2.
Okay, so I'll take the first and the third finding, and Ben will cover the second one. So our first finding is that there have been a few studies in recent years that have looked at whether we can include the effect of unocculted active regions, spots or faculae, and extract properties of the planetary atmosphere simultaneously to the stellar properties. But we've barely scratched the surface here. And although there are some good studies in the literature, really a lot more work needs to be done to look at the full phase space of how these regions can affect spectra, to see whether it's something we need to blanket consider across the board, or whether there are some trades to be done in terms of precision and resolution and wavelength range, where we don't need to worry about this. So to illustrate this, if we move to the next slide. So I really like these figures from Arazi Pinas's work a few years ago. So on the left here, what it is showing is a model spectrum of a model transmission spectrum of a hot Jupiter, where the atmospheric properties are the same for all of these models, and all that is changing is the background temperature of an unocculted region, where the models that you see at the top there with the greatest slope have unocculted spots, and the one down at the bottom that is sloping downwards has unocculted faculae. And essentially all that is being shown here is that if we have an unocculted region, the spectrum that we observe is the product of the atmospheric spectrum of the planet and this contamination factor that you see on the right there, that we've heard about in a few talks already. And we can visually see here that at longer wavelengths in the infrared, this factor tends to around 1, but at shorter wavelengths, the impact is much more significant. And down at the bottom there is just the functional form of this contamination factor, which is essentially just a weighted sum there of the fractional covering area of each of the active regions, modulated by the ratio of their intensity relative to the photospheric temperature. So as to how this all works in a retrieval framework, if we move to the next slide. So here we are just illustrating for a very simple toy model of a hot Jupiter that has sodium and potassium features in the optical and some water bands in the infrared. And it also has some unocculted spots covering, I think I put in there 10%, 5% actually, of the photosphere's area. And the spots have put in this steep slope that we see in the optical, but also some of those little wiggles that you see at the shortest wavelengths are also induced by spots. So if you have sufficiently high precision, you may expect that you would be able to disentangle a slope due to an atmospheric haze from unocculted spots, for example. But this is an example of one of the areas where more work needs to be done to look at how precise the data needs to be able to be to disentangle that. So on the corner plot that you see on the right there, showing the correlations between the extracted parameters from this retrieval, we can see that, at least for this toy model, there don't appear to be strong correlations between the composition parameters here, so how much sodium, potassium, and water there is, and the stellar parameters, like the fraction of the spots. There are certainly some correlations between the stellar parameters, like between the covering fraction and the spot temperature that we see there via that kind of curve-like shape in the bottom right. But this looks promising in this particular case, that perhaps for many of the key parameters of the atmosphere that we want to extract, there don't appear to be very strong degeneracies with the unocculted regions. This demonstration does assume, though, of course, that we have a perfect model, that we have the right stellar spectra, because this framework here does require you to load into the retrieval some stellar models, and you're a priori assuming that they are the right description for the particular star. So there are many challenges yet to be solved, but hopefully this is illustrating that we can infer both the planet properties and the stellar properties from the observed transmission spectrum itself, given sufficient quality data. So if we go to the next slide, that was just a toy model that we were taking a look at here. Here is some real observations. This is a set of the spectra from David Singh's 2016 paper that were all retrieved by also in Arazi Pinas's paper, to look at trying to sort these spectra to see if there's any evidence already in existing Hubble, STIS, and WISI-3 observations of these unocculted regions. And what Arazi found in the top left there is that two of these spectra, WASP-6b and 39b, show some evidence of unocculted spots at around about the 3 sigma level, while some of the other spectra, like the ones in the bottom right highlighted in red there, appear to be fit fine by a purely planetary atmosphere model. So there's already potentially some signs with existing observations of unocculted spots. And if we move to the next slide, we're now reaching the point that a number of studies are starting to see signs of unocculted faculae popping out in retrievals. So in this upcoming study by James Kirk on the ultra-hot Jupiter WASP-103b, you see this characteristic slope down towards the short optical wavelength, which is a key discriminating feature of faculae. Indeed, the purple curve that you see here is what the planet's atmosphere spectrum would look like if there was not any stellar contamination. So we can see that this slope that goes all the way down from the near infrared all the way down to the optical is key evidence here, in this case at around the 4 sigma level of unocculted faculae. So if we're seeing this already with both ground and space-based observations, this is a key indicator that this is going to be increasingly something we're going to need to consider for retrievals in the imminent era of JWST. And now I'll pass back to Ben to go over finding number 2.
Yeah, that brings up our second finding, which is that these approaches that we advocate for rely on stellar models, and thus their accuracy is necessarily limited by the model fidelity. So we point out a few ways, paths forward where we could test this model fidelity or potentially improve on models. Very generally speaking, we think that there's work to be done to further test and develop models for cool stars, which would be very, very useful for this work. There's work to be done to assess the impact of this common technique for stellar and planetary retrievals, which is using stellar spectra with different temperatures to approximate the spectrum of an active region. And finally, we find that there's further work necessary to develop model spectra specifically for active regions, and particularly faculae of different spectral types. So I'll just go over a couple slides that hopefully illustrate where these conclusions come from, these preliminary conclusions. The first is this slide kindly provided by Aisha Ayer and Mike Line from a work in PrEP, in which they point out the disagreement among stellar spectra for cool stars. This might not be news to people who work on stars here, but for people on the exoplanet side of things that sort of treat these model truths as these models as truths, we might take a bit of caution. So the three panels here show spectra of three cool stars, 2300 Kelvin, 3000 Kelvin, and 3500 Kelvin, for taken from different model grids, about 8 or 10 model grids for each of these. And you can see by eye that there is quite a bit of disagreement about the emergent spectrum of these stars from the different grids. And particularly, I'd like to draw your eye to the bottom left plot here. For the very coolest stars, there's about a 20% discrepancy in the strength of water absorption at the 1.4 micron mark. And for exoplanet astronomers, that should ring some bells, because that's where we typically infer the presence of water from HST WIFC3 observations. And it's been pointed out in the literature that among cool stars, there can be water vapor present in the spots, and that can introduce a TLS or contrast effect owing to unocculted spots. So we should be wary of the fact that there's such disagreement out there, that the dispersion of these models is so large. This has an impact on the derived planet properties that we get out of these retrievals. And this is illustrated in a published work from Aisha Ayer and Mike Line, in which they investigated the impact of unocculted spots on James Webb spectra. And they make a very interesting point with this plot. On the left side here, on the top left panel is showing the disintegrated stellar spectrum as a function of wavelength for a single star with 12% spot coverage, but using two different model grids to produce that spectrum, the Phoenix and Phoenix Aces models. On the bottom left plot here, they show you the transmission spectrum, the observed transmission spectrum, encoding the impact of the stellar atmosphere, the heterogeneous stellar atmosphere, and the planetary atmosphere for these two different model grids and a input planetary model spectrum. And you can see that the impact is different between the blue and the purple lines. And they take this analysis a bit further, which is very interesting. And they do a retrieval on one spectrum that was generated with the Phoenix Aces model grid, using in their retrieval framework the Phoenix model grid. And that's shown by the gray line there. That's the retrieval, the best fit retrieval model. The right panels here show the impact of that, showing the input and posterior distributions of three parameters of the planet: its temperature, its metallicity, and its C/O ratio. And you can see that the posterior distributions are all highly biased away from the input values in this case. So if the difference between our model grid and the actual stellar spectrum is something like the difference between the different model grids that are out there, this is an effect that we should be really concerned about when it comes to active cool stars and in retrieval frameworks. There might be some way forward, though, as Ryan has pointed out to me, and that even in the best fit model here versus the data are precise enough that you should be able to tell that there's something else going on, that your model here is not in fact a good descriptor of the data. And so we should keep these sort of things in mind when we get our hands on very precise James Webb spectra. The final point related to preliminary finding 2, which advocates for more work to actually model the spectra of active regions on other stars, is that model spectra of these active regions are becoming available. There's more and more examples of this in the literature, which are very promising. So here are two examples from recent works. On the left, we have the spectra of faculae on a sun-like star with different magnetic field strengths as calculated using the Miram code by Norris et al. And on the right, we have faculae and spot and the total disk spectrum of the sun using the satire code as calculated by Witzke et al. These types of studies are very important for exoplanet transmission spectroscopy. And so far, because of obvious limitations, they're mostly focused on stars like the sun. But as we heard in talks earlier today, people are branching out and looking at spectra on other spectral types. In particular, we find that understanding faculae spectra on stars other than the sun will be very important for the data that we're going to get from space-based transits. And then I'll hand it back to Ryan to talk about our last finding.
Thanks for that, Ben. So our third finding concerns the importance of short wavelength observations. And what we mean by this is that unfortunately with JWST, the lowest we'll be able to observe is down to 0.6 microns, while we can push down to lower blue or near UV wavelengths with Hubble and various ground-based instruments. So, and if you've noticed any common theme with all our findings so far, there's a lot more work that needs to be done in all of these areas. So if we move to the next slide. So so in these two figures from two of Ben's papers, what we're illustrating here, and if you just move forward to highlight them, the region bluewards of 0.6 microns that we can't access with JWST is a region where the impact of unocculted spots and faculae is increasingly prominent. And we also saw that in the earlier figures in preliminary finding 1. So the question is, how bad is it if we don't have such observations? Do we need to have complementary observations alongside JWST, or can we get away with just 0.6 microns and onwards? And this is a really crucial question that a lot more work needs to be done on addressing. So to illustrate some of this with specific examples of real observations, here we go. So here is a spectrum from an upcoming paper led by Alexander Rafke, who's a graduate student at the Technical University of Denmark. And Alex has done some really nice work on this hot Jupiter WASP 79b, extending the wavelength coverage of this spectrum down towards the near UV, down to 0.3 microns with Hubble STIS. And what we see here is, again, evidence of this downward sloping signature towards the short wavelength optical data, indicating unocculted faculae. But in this particular case, the wavelength coverage goes down low enough that you see there's that little kind of step upwards at around 0.35 microns. And this is also a spectral signature from unocculted faculae that has been imprinted into the overall transmission spectrum. And although there's only one data point here sampling that shortest wavelength, that data point does indeed show this upward step. So this is potentially an indicator that short wavelength data can really be crucial to increase the confidence in inferences about unocculted spots or faculae. And if you move forward, Ben, so, and in this paper, which hopefully will be up soon, we're just addressing the referee comments at the moment. But what was done in this paper is 3 independent atmospheric retrieval codes were run on this spectrum to see how robust the inferences on stellar contamination are. And although all 3 codes make very different assumptions about the planet's atmosphere, they all agreed that you have to have unocculted faculae with reasonably consistent parameters. The uncertainty on the spot parameters, or sorry, faculae parameters, I should say in this case, are very large, everything from 5% covering fraction to 25% is supported within the 1 sigma uncertainty intervals. So perhaps it's a case where you can tell that there are faculae, but without some independent observations, perhaps out of transit stellar observations, is going to be hard to infer from the transmission spectrum itself some of these stellar properties due to things like the temperature contrast, area fraction, degeneracy. So there's another example on the next slide. So this is going back to James Kirk's paper on WASP 103b. And one of the nice things that was done in this paper was there was an attempt to quantify how important the optical short wavelength data is. So we have a table that will just pop up in a second. And there's a lot going on in this table, but essentially what's most important is down at the bottom, which is showing that if you only retrieve the near-infrared observations, in this case from Hubble WISC 3 and Spitzer IRAC, in this case, you can still infer that you need unocculted faculae in the retrieval, which comes from that gentle downward slope, which is still visible in the near-infrared. However, the statistical significance jumps up from about 2 sigma to 4 sigma if you add that short wavelength optical data. So there's a lot, these are just specific examples, and a lot more work needs to be done on systematically surveying exactly what the utility is of this short wavelength data and how much it can bolster or boost any inferences that we obtain from pure infrared JWST observations. So, so that wraps up our finding number 3. And there are a couple other topics that we're also looking at in our subgroup to try and extend this a little bit, since it's a very new research area. So, for example, looking at some of the areas that Jim was talking about earlier about the utility of out-of-transit spectra. And all of the results that I have shown you so far here, we're all looking at where we just consider one unocculted population, either spots or faculae. And there's a lot more work remaining to be done looking at whether we could simultaneously retrieve both spot and faculae properties at the same time. And now I'll pass back to Ben for the conclusions.
Yeah, just to make sure that we have some time for conversation, I might not iterate through this again, but essentially here are the 3 conclusions that we'd like you to leave with. These are the 3 preliminary findings from this group. Conversations are still ongoing, and we are hope if you have any input, please reach out to us and let us know. And we are going to continue these conversations for the next few months before finalizing our report to NASA. Thank you all for your attention.
Thank you, Ryan and Ben. It was great. We have questions from Slido. Sasha asks, is there any hope for an instrument which can detect ozone bands in the atmospheres of rocky planets? You know, given what you've said, what are the chances for that?
So maybe I'll start, and Ryan can chime in if he has something to say. I think that it's not a foregone conclusion. I think that it's something that we certainly need to be aware of. There are promising results from the limited results that are there in the literature. And for example, I'm thinking about Aisha Iyer and Mike Lyon's study from 2020, which is the first one really that has simulated, the first one to my knowledge has simulated James Webb observations of planets around active M dwarfs and injected spots and tried to retrieve. And they find that at the precisions that we're going to get from James Webb, there will be noticeable differences in the spectra, and that we won't be able to completely explain away an atmospheric feature from a planet by invoking unocculted spots. And the unocculted, on the other hand, the unocculted spots won't completely preclude us from measuring atmospheric features, but it's something that we need to take into account when we're trying to analyze the spectra.
I would just
and it's something that we need to study more.
Sorry.
Go ahead, Ryan.
I would just add a fun little advertisement to that if you want to go for those O3 features, in particular the very strong bands that you see in the near UV, in the near term, looking for rocky planets around white dwarfs would be a great way to do it, due to the large contrast ratio, and it would be very easy to detect those ozone features in the near term but we don't currently know of any of those planets. So yeah, as always, more work needs to be done.
Yeah, that's up to the observers to find. That's good. There's a second question here, which is related to, it says, how does unocculted active regions versus Rayleigh scattering impact your planetary abundance measurements / correlations? I think here thinking also on error bars, for instance, is that impacted as well?
You want to take that, Ryan?
Yeah, so in the simulated retrieval exercises that I have done, looking at, actually in the toy model that I was showing earlier, that model did include Rayleigh scattering, but the spot just completely dominated it. And so there weren't any problems in inferring the abundances there. It can be a little bit more challenging if, yeah, here we go. So it can, so you see all the abundances are correctly retrieved there and there aren't strong degeneracies there. If you, however, had a haze in the atmosphere that produced a much steeper slope at the same time as you had spots, you can still disentangle the haze parameters and the planetary abundances, but it relies on, I mean, you can see from the magnitude of the error bars here, which, if I recall, were 50 ppm in this demo. A haze, in many cases, is just kind of a reasonably featureless slope. Depending on the wavelength coverage you have, and if you have me scattering, there's lots that you can add. But if you have good enough data to see those wiggles that have been imprinted by the spots, then you shouldn't experience a degeneracy between the two. But this is a very qualitative statement at the moment, and it'll be really nice to see a study looking at how precise the error bars or the spectral resolution needs to be able to definitively differentiate between hazes and spots.
Thank you. We're at the hour, but I just want to put one question out there from the 3 most rated. There's other 2 questions you can go and check, which is related to WASP 103. Prajwal says, like, looks like there's a bump. Where do you expect the soil line to be? Can you still detect strong features despite the contamination?
Yeah, that's a good question there. And yeah, that is indeed a narrow band centered exactly on the sodium feature. In this particular case, the reason that sodium doesn't come out of this retrieval is that you see that there are other data points that don't show evidence of the pressure broadened wings of sodium that have a slightly wider bandpass and also cover that feature. So, yeah, so the retrieval does not identify sodium here because it's not picking out the wings.
All right. Well, thank you both for this talk, and thanks everyone for today's session. It was great. I think we all learned a ton of this extremely important topic on stellar contamination. So just want to give a huge shout out to everyone for this enlightening discussion.